Okay, let's look at an example for the evaluation of average heat transfer coefficient over a flat plate. And let's say we have a flat plate with the length of 75 centimeters, that air at 20 degrees C is flowing over the plate at 35 meter per second and at atmospheric pressure. The plate temperature is kept constant at 60 degrees C. This could be in this can happen in any configurations. Let's say you have one of these environmental chapters, the chamber that you want to keep everything at the 60 degrees C or something like that, and then it has a thin wall, or the plate wall just stays at the 60 degrees C, or you want to put it at 60 degrees C and then you put a fan. Air is just like flowing over that plate. And as a schematic of that one, this is the plate that we are dealing. The length of the plate is 75 degrees centimeter. Temperature of the plate, Ts, is 60 degrees C. And we have a fan, or it's just outside that air is flowing. So the air is flowing with the velocity of 35 meter per second with the temperature of 20 degrees C. And pressure is given at 1 at 18. So air is flowing over this flat plate and we're going to find what is H. For this problem, I can list the knowns as what we know here. We know surface temperature, 60 degrees C. We know fluid temperature, 20 degrees C. We know fluid velocity, 35 meter per second. Pressure that is flowing, 1 atmosphere. And the length of the plate, 0.575 meter. These are knowns. In terms of assumption, what we can say, this is a steady state condition. Assuming that one, we can assume properties, whatever that you're going to use, remains constant. No radiation that happens here for the heat transfer. And the last assumptions that I'm going to make here is this is an incompressible fluid. What we are going to find here is H of L, average. So first thing first, we need to find out properties. Now we evaluate properties, evaluate actually fluid properties or properties at film temperature. So Tf is Ts plus T infinity divided by 2, 60 plus 20 is gonna be 40 degrees centigrade, which is equivalent to 313 degree of Kelvin. Now having this temperature, if we go on pressure, we can go to the table, is 1.13 density of air. Viscosity of air is 1.91. 91 times 10 to power minus 5 Pascal second. Specific heat capacity is 1.007 joule per kg Kelvin. And I need a thermal conductivity, which is 0.0272 watt per meter Kelvin. And we can read the Prandtl number or evaluate Prandtl number as 0.70 for air. So these are the properties that we are going to use. Now, the other thing that we need to define for this plate is the flow regime. And remember the equations for the convective transfer or Nusselt number, the dimensionless form of that, are based on the flow regimes that happens. So to do that, we need to find flow regime. So one of the simplest way, just for a quick check here, is, let's say this is x0, and that's the x-axis, and then x equal to L, is to find what's the Reynolds number at the end of the plate. Remember, Reynolds number is changing. It's like rho u infinity L divided by mu, and or Reynolds number at any x location is going to be rho u x divided by mu. So I know along the x for the flat plate, Reynolds number goes up. So I can find the highest value of Reynolds number by considering the rear edge of the plate. So if I do the evaluation, density was 1.13, u infinity 35, L is 75 meter, and viscosity is 1.1 10 to power minus 5. One thing that you need to be very careful is in terms of units. I didn't really put the units here, but the units are very consistent here, and all of them are going to cancel out. So Reynolds number is a dimensionless number, and the units should be consistent too. So it's going to be 1.55 times 10 to power 6. Now for a flat plate, we had a critical Reynolds number. We were saying Reynolds number of x, and c, the critical one was 5 times 10 to power 5. So the value of Reynolds L is greater than this critical value. What it means here, a portion of plate is exposed to the turbulent flow. So if I have this plate, and this is the flow of air that's coming. So initially I have a laminar flow, and then we have transition to the turbulent flow. So I can assume this is laminar, not really considering the transition zone, and this is the turbulent boundary layer. And this is the place that I have RE, C, and X is going to be 5 times 10 to power 5. Now, if we replace here, if we use this Reynolds number in the equation that, and C rho u infinity xc divided by mu, from here even we can find what is the location that the transition from laminar to turbulent happens for this flat plate. And since we have mix of both of them, and we are using this critical one, we can use the combined, or we should use actually. So let me just put a little note here. We have both laminar plus turbulent here, or the mix kind of convection that happens around this place. So we use combined or mix laminar plus turbulent equation. And for that one, what we have is Nusselt number L, the average, which is HL over K, 0.37, Reynolds number to the power of 4 divided by 5, minus a constant value A depends on the critical Reynolds number, parental to the power of 1/3. Since we are dealing with the flat plate, and most probably for most of the case, we are gonna use the same critical value. So you can simply replace this one by 875 as shown in the previous part of the lecture. So if I do the replacement here, it's gonna be 0.035 times 1.55 to the power of 6 power of 0.8 minus 871 times 0.7. So if you do the math here, the Nusselt number, the average Nusselt number is going to be 2180. So from here, we can find HL, which is Nusselt number L times K divided by L. So 2180, K was 0.0272. Remember, the unit of K is watt per meter Kelvin divided by 0.75 meter. So HL is going to be 71.1 divided by watt per meter square Kelvin.